Good morning, mathematicians. I don't know what I want to talk about today. I mean, presumably more D module stuff. But I don't know where to go next. Oh, there was something I was gonna do a calculation, I think. Offline. And then I can make sure I do it right online. Oopsies. I am streaming, it says. Where's my video? Where's my live? I was gonna do a calculation, I think. Offline. I guess I'm pretty delayed today. Um, yeah. Well, maybe I'll talk. Oh, there is some computations I could probably do off the cuff. Um, Maybe I'll talk a bit about the Riemann-Hilbert correspondence. So we have D modules, right? What have we talked about? How to go back and forth between D modules and a quasi-coherent sheaf with a flat connection. What else? What else are we gonna look at? Well, um, yeah. I guess one thing I'll just mention it. Uh, so we're interested in constructibility. What does this mean? So often we will have some stratification of a variety, and a sheaf is said to be. So we have local systems, right? That's one part of the story. But then another part of the story is that we have a sheaf where the restriction to each subset is a local system. In particular, for my research, the cases I'm interested in is I usually have a G variety that stratifies X into finitely many orbits. And so I would like to understand sheaves that are constructible with respect to this stratification. And in particular, we want to think about equivariant local systems, equivariant, well, things. So local systems definitely come into play here. Well, one of the things is we would like to understand also not just D modules on X, but equivariant D modules. So the actual defining condition is more technical and precise than what I'm going to say, but of course, the very rough idea is that, of course, each element of our group gives an action on X, right? And so somehow, whatever a D module is, or an equivariant sheaf, or an equivariant local system, it should somehow have some compatibility with this, right? So like something like maybe if you look at you pull back your sheaf along this action of G, that somehow compares to the original sheaf, right? Maybe you have an isomorphism or something, and maybe you have a family of isomorphisms, and those are compatible. There's some sort of compatibility of morphism condition or something, right? It's a little different than that. Maybe I'll touch on it in a moment, but I guess let me just say that the way that we single out the D modules we're interested in is it turns out that every... I wonder, is chat working correctly? No one's here yet, which is weird. Maybe I need to re-pop out chat. Oh no, I guess just no one's actually here. Not used to that. Anyways, oh, you're here. Hello, Arad. Hello, hello. Oh, hello, Kine. Okay, nice to see you guys. Okay, yeah. So we've got this stratification. How do we find all of the equivariant D modules? Well, it turns out that they can all be built from a procedure called minimal extension. And so minimal extension, here's what it does, is basically it says the following. So you take an orbit, you take a stratum, you take a local system on that stratum. So in the equivariant case, we take an equivariant local system on the stratum. So I'll talk about that in a moment. Actually, maybe we should go pull up the proper definition together. Actually, maybe I can remember it. No, there's some details I'll need to look up for the full proper thing. But, and anyways, the recipe says that as you run over all of the irreducible G equivariant local systems, and as you run over all the orbit, then the minimal extensions of those things will enumerate the simple D modules. So that's how you get all the simple G equivariant D modules. Okay, well, what is this minimal extension functor? It's kind of a nightmare, to be honest, to define. It's really nasty, in my opinion. However, there is, there's a theorem that basically characterizes the minimal extension in terms of three properties. So I think that's one of the things I was meaning to do, was to there's these examples of D modules I had above, the examples which were quotients here. So I wanted to realize these as minimal extensions of C under this stratification. Which, yeah, again, doing the actual computation, not so fun, but just verifying that it satisfies the sort of three conditions that uniquely determine the minimal extension. That was the plan. So maybe I'll do that at some point. But yeah, that's could be a nasty computation to dive into. Okay, well, what about the G equivariant local systems? Well, so I'm thinking we might need the connectedness. I can't remember what role connectedness plays, but very roughly, we can look at it this way. So you know, we've got our local system representation of the fundamental group correspondence. And for any orbit, right, Gx, G mod the stabilizer gives you an isomorphism of onto the orbit, right? And so therefore, one gets a covering if you look at the connected components of you mod out by the connected components, you then get a covering of this, which in turn gives you a covering of the orbit. And Well, of course, there's a whole. So I've sort of been loosely going back and forth between the algebraic and analytic perspective. But of course, the other way to think about fundamental groups, right, is that the fundamental group of your space is the automorphism group of the universal cover, right? And basically, all of your if you have a cover that factors through, then what did I write? 0 should be like x or something. Then the automorphism group of that cover, I can't remember which way it goes. It's a quotient. It's a quotient of the fundamental group. Yeah. Well, yeah, I think yeah, I believe it should be a quotient. Yeah, it's like Galois theory, right? Um, but that's only for normal covers. Oh, I got my. It's been a while since I actually did the covering correspondence, but so. Anyways, the point is that this cover, then the group, the group corresponding to this cover, the like automorphisms of this cover, is then going to be the stabilizer modulo the connected components. And so, just like how we want to, and so this group should factor through the fundamental group via this correspondence. So I guess we should have like a map here or something. And so basically, if we want an equivariant local system, we want to look at representations of this group. And we want to pull back those representations to the fundamental group, and then we can apply our usual local system procedure. So do we end up really only needing to classify D modules on the group itself? No, definitely not. Well, so I should say, yeah, so definitely not, it doesn't have to do with, well, does it have to do with D modules on the group? I don't think so. I mean, I've never worked with, well, I shouldn't say never, but I don't really work with D modules on the group itself. But let me pull up our good friend Achar here, just to make sure I get some of the definitions not wrong. Yeah, it's just more that you're looking at a representation of the component group, and then you pull that back. So let's see, we should be in chapter 6. Yeah. So I mean, one of the things. So, I mean, sort of yes and no. So, like, you can see here the definition of a G equivariant sheaf, and we can use the same definition for perverse sheaves and D modules. A G equivariant sheaf on X is a pair where, so F is just an ordinary sheaf, and then here the pullback is, oh, he didn't write it down. I'll write it down here. So we have from G cross X, right? There's two ways to project down to X. You can just take projection on the second factor, or you can take the group action, right? You can have G act on X and take out that thing, right? So, of course, this relates, much like we talked about this sort of slightly more naive version here, relating the action of G to the unacted thing to talk about some sort of equivariance. We can do a similar thing here, and so the demand, so an equivariant sheaf will be a pair where F is an honest God sheaf on X, but then we can pull it back. And I forget which way I forget which direction he puts the isomorphism in. I mean, it kind of doesn't matter. It's an isomorphism, but then you pull back F in two different ways, and so now this is a sheaf on G cross X, and you have a morphism of sheaves on there. So technically, I mean, the definition of an equivariant sheaf, D module, blah, 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 does have something to do with that corresponding concept on the Cartesian product of G and X. You just thought since the strata are orbits, we can pull back from them to the group. But I guess at that point it doesn't really matter because they're already local systems. Oh. Yeah, I didn't even think about doing that. Yeah, that's true. I guess we can, but you're right. It definitely... Right. And then, yeah, maybe the fact that they're local systems removes the dependence on the base point. Yeah. But that I'm not sure what to do after that. I'm not sure what to make of that. Yeah, you can definitely pull it back. Hello, Argya. Welcome back. Yeah. That is interesting though. I do wonder what can be done with that. Yeah. Yeah. So that's our proper definition of equivariance. Let me let's go over to a char again and just find the correspondence. I mean, there's more going on here, right? There's, you got to define a morphism of equivariant sheaves, and there's, well, I mean, okay, I guess you can see from the diagram, it's kind of the obvious thing, right? But there's one other thing I wanted to talk about, the equivariant sheaf characterization in terms of fundamental groups. Yeah, here we go. Right, it's down here in this remark. Yes, aha. So I knew that G had something to do with being connected. Yeah. So it is true. It is true in general that your category of local systems, just for any algebraic group, your category of equivariant local systems of finite type are going to correspond to finite dimensional representations of the component group. However, what I was saying in the case of the fundamental group, that's where we use connectedness. So if G is connected and X is a homogeneous space for X, so basically, this just means X is of the form G mod a stabilizer. Right. So it's saying that we get the following exact sequence if X tilde is the cover that I wrote down before. Then we have a short exact sequence. So like I said, this is the automorphisms, or I guess the deck transformations, one would say. And we get this short exact sequence. Yeah. Yeah. So, and then there's this, yeah. That's all. Okay. Maybe that does it for today. I don't know. I do still have some coffee left. What's perv G? That's equivariant perverse sheaves. Or a perverse gangster, if you like. So, Tony, I don't know what point you showed up. I don't know if you saw this part about pulling back, talking about an equivariant sheaf as being one that where you have an isomorphism between these two different ways of pulling it back, but you can play this exact same game for perverse sheaves, where again it's a pair. The first thing is a perverse sheaf. The second thing is a morphism. But now, of course, this is all happening. A perverse sheaf is a complex of sheaves, so this would all be happening at the derived level. Yeah. So I don't know if you're familiar with perverse sheaves at all. But yeah, those are complexes, special complexes of sheaves. So they live in the bounded, derived, constructible category. So that was something I talked about earlier at the start of this. The word constructible basically means, I guess this is something else I do want to say. So constructibility means that if you have some stratification of your variety, then your sheaf is said to be constructible with respect to that stratification if the restriction to each stratum, and in the cases I care about, this will be coming from an orbit, is a local system. The constructible derived category is, we have sorry, blanking. Need more coffee. Hello, Matthias. Hello, Paul Maurice. The constructible derived category says that for any complex in here, each of so you take cohomology, but then, it's a complex of sheaves, so you can take a sheafy cohomology. And then the constructible derived category says that each of these are constructible as well. H cross I, Hi are subgroups of G where phi is trivial. Huh? Daysin, good to see you again. But also, are you asking a question? Or is this a semi-direct product? Seems like a semi-direct product. Yeah. So yeah. Oh, your new way of saying hi. Oh my God, I didn't even that. Wow, that went right over my head. That went right over my head. Good one. Yeah. So, anyways, speaking of perverse sheaves, we were talking about constructible sheaves. Maybe we should talk about some cohomology with compact support then. Maybe. I saw this really cool thing. I posted it on Twitter. Where was it? It was some document. Some document I had found. I'm gonna go to my profile. Oh, I'm not verified. Yeah, this picture. I'd never seen this before. But I think it's so cool. It's a very simple way to explain the differences between cohomology theories. So it's all just performing different push-pull, or I guess I should say pull-push correspondences between the different cohomology theories. So I think basically the idea is this: in each case your map, you take the map P from your space to the point, and then we can see. And so then each of these operations then on returns a complex. These are all in the derived sense. So ordinary cohomology is you pull back and you push to the point. Cohomology with compact support is you pull back and then you do exceptional push forward. Ordinary homology is exceptional in both cases. And then Borel-Moore is exceptional pullback and regular push forward. And I don't know. I think this is so neat. It's just such a neat way to have a little comparison between all the like popular cohomologies. What a neat little thing. Yes, I think it does essentially come down to definitions and growth and Dieck duality, yeah. Constructible sheaves are just, you've got some stratification and their restrictions are local systems. We'll get into some computations soon enough. In this case, well, of course, the constant sheaf is constructible, right? Take the constant sheaf on the entire space. Of course, if you restrict it, I mean, in general, take a constant sheaf on a space X, restrict it to a stratum, this will be the constant sheaf on that stratum, which is certainly a local system. Take the constant local system, I should say. Yeah, so that's a prime example. So yeah, what do I want to do? Turns out I want to talk about the Riemann-Hilbert correspondence at some point, which will take us from D modules over to perverse sheaves, and it turns out this is actually very computable. I wrote down some computations the other day, which is pretty nice, and I was able to so I want to talk about this sometime soon. And then also, I mean, there's a reason. There's a reason I talked about this, and I've talked about, I talked about some connections and local systems. So previously, so So before I go, let me just talk about this idea. So if we look at this idea of the stabilizer, the component group telling us all the equivariant sheaves. So let's imagine that our group G was the non-zero complex numbers and X was the complex numbers, and that we had G acted on X like this. Wouldn't I say perverse sheaves categorify cohomological truncation functors? I don't know what you mean by that exactly, because they're already pretty categorical. So I would not say that. Aligned with the middle perversity via the T structure. I don't think what you said really makes a ton of sense, to be honest. But it is true that perverse sheaves are defined to be the T structure, the heart of a T structure, of a particular kind of T structure. And you could say on the orbits, which themselves are smooth, it turns out that the perverse sheaves are just shifted local systems. That is also true. But that's how I would say those things. You just mean that the perverse sheaves filter data from local systems and cohomology in a way that matches the stratification. That, sure, yeah, I guess you could say that, yeah. Like a structured way to glue the pieces together, yeah. You wish the streams were done with voice instead of text. Typing on the chat is already confusing for even cooking streams. That's an idea. Maybe that could be a thing. If I launch a Patreon or something, that could be like the Patreon, like a couple days a week, I could have like a chat stream, like a Zoom something. Could I do like Zoom and live stream? Yeah, how do I set all that up? I probably could. And then people could just chat freely and draw stuff. Maybe I'll do that. Oh yeah, I'm going to think about that. There's only so many hours in the day. Also, I need to figure out how to like design and make merch. I have definitely not read Deline Vey 1. I have not. But let me just mention in this case, X has two pieces of strata. Let's call these C0 and C1. What is the component group? So we might call it A0. The component group, which keeps track of our local systems, is trivial. So there's only one local system, which is the constant local system on the orbit Why read V1 when you can read V2? Why not read them both? Hold them both open and have one eye trained on each book. Why not that? But if we look at the stabilizer of 1, which is in the other orbit, we can see that that forces t to be plus or minus 1. So in other words, the other component group is z mod 2. So we know that there's 2 local systems on here, 2 G equivariant local systems. So again, we always have the constant sheaf. But remember, I computed in a previous video we have the representation that sent an integer to plus or minus 1. Well, notice that this factors through z mod 2, which is our non-trivial fundamental group. See, days ago, this was all cooking up here. I was going this direction intentionally. I computed already this character, and I found that there's a non-trivial local system here corresponding to the quadratic character, and that was the local system. That corresponded to solutions to this differential equation. And we saw, this different. So like I said, we also talked about how if you just take OX and you're on affine space, then the exterior derivative will be a connection. And so in both of these cases, we have corresponding to this just OX and the connection, and the respective sheaves just arise as the kernel of that of the exterior derivative as a connection. We also talked about how this local system arose as the kernel of a connection basically defined by this differential equation. And so from here we can go on to cook up D modules, and here we can go to cook up D modules, and in the procedure described last time. And then finally, hopefully in the nearish future, we'll go through the minimal extension and find, guess what? It's no coincidence, the D modules I talked about previously, the corresponding D modules will be this one, coming from this will be the minimal extension of this one. The minimal extension of this one will be this one, and the minimal extension of this one will just be this modulo its defining differential equation. Yeah. If only we could go further away from the sun and make the days longer. Yeah, that would solve all my problems. But then move the Earth back. Actually, does that really? I don't think that that wouldn't make the days. Actually, that wouldn't affect the length of days. It's how fast the Earth rotates. Yeah. Ooh, global Lefschetz. Yeah, I don't know anything about that though. I know that there's stuff about, wrapped up in these perverse sheaves, the like hard Lefschetz theorem and stuff, but I don't really understand those things so well. Yeah, and speaking of the vague conjectures, there are 2 books. What are they called? I forget what they're called, but there are these 2 books. It's like, oh yeah, if it's my favorite typo in all of math. It's like I think book 2 is like perverse sheaves and the L apostrophe attic Fourier transform or something like that. Best typo in all of mathematics. Anyways, and they really do a whole bunch of this crazy stuff, and relate it to the Weil conjectures. Where do you learn all of this stuff? To surprise your dynamical systems prof? Would your dynamical systems prof care about any of this stuff? I don't know. Well, so I just mentioned there's these two books by Freytag. I'm not even gonna try to spell his name, and Kiel, and one of them is called like Perverse Sheaves and the Laddick Fourier transform. Of course, I opened up Achar's book, Perverse Sheaves and Representation Theory. That's also a great source for perverse sheaves and D modules. Eckhart Kiel, that's who it is. I thought it was Freytag Kiel. What am I? Huh. If you push the Earth backwards, wouldn't conservation of angular momentum actually make the days shorter? I don't know. That's too applied for me. And on that note, I'm going to leave for real this time. And maybe by next time I see you, which is likely tomorrow, I'll have done some homework to properly compute the minimal extensions online. But even if not, we will talk about the Riemann-Hilbert correspondence and compute it, I think, maybe.